As you might guess, we're not always going to be given a graph where it's easy to spot the local minima and maxima of a function, right? So a lot of times we're just going to be given a formula for the function, and we need to be able to figure out where are the local minima and maxima of the function. So let's start here with the local extreme value theorem. The local extreme value theorem just says that if the function has a local maxima or minimum at a point, and the derivative of the point at that point exists, then the derivative has to be equal to 0. So, I think that makes sense. You probably saw it with the graphs. If we have a function where the derivative exists, right, and it's increasing, and then it starts decreasing, well, our derivative is switching from positive to negative, and we get a local maximum. And the other case where it's decreasing and then it starts increasing, right? The derivative goes from negative to positive, and then we get a local minimum, right? And at those points where the local extrema occur, the derivative is 0. Now, the converse of that statement is not true, right? If the derivative is 0, we can't conclude that we have a maximum or minimum at that point. But what it tells us is that we have candidates for the local minimum and maximum. So now those candidates are called critical points. And the way that we find critical points are as here. A critical point is an interior point in the domain of the function. It's called a critical point if the derivative is either equal to 0 or the derivative does not exist. Okay, so those are our critical points. Either the derivative is 0 or the derivative does not exist. And those are our candidates for local minima and maxima. All right. And then finally here we have a kind of a step-by-step process of finding the absolute extreme values on a closed interval. Now that's important. A closed interval. Let me highlight that. Closed interval. All right, because this is important. We're only dealing with closed intervals now. So if we have a closed interval, then what do we need to do to find the local minima and maximum? First, we're going to identify the critical points of the function on the interval between a and b, right? So what we're going to do is just find the derivative, set it equal to 0, find the points where the derivative is 0, and also look at the domain of the function and identify any points where the derivative doesn't exist. Okay. So we got to remember to do those two things. And then number 2, we're going to evaluate the critical points and the endpoints. So we're going to evaluate the value, find the value of the function at the critical points and at the endpoints of the function, right? Because we're dealing with a closed interval. So we're going to evaluate f of a and f of b. And then all we need to do is compare the values, right? The values of the function from step 2 and identify, okay, which value is the biggest and which value is the smallest, right? The value of the function, right? And then those will be our absolute maximum and absolute minimum values. All right, so let's try out this process. So first of all, let's look at this function here. Now, the first step is to find the derivative. So we're trying to find the critical points, all right? So first step is to find the derivative, f prime of x. Okay, now I could FOIL that out, but since I know the chain rule, I'm just going to say this is 2 times x minus 1, and then times the derivative of x minus 1, which is just 1. And I'm going to set this equal to 0. So I have a critical point. I'm going to say critical point at x at x equals 1. All right, so now I've identified the critical points. Now I also want to look at the derivative and see if there are any points where the derivative is undefined. And I see that there's nothing. On 0 to 3 anyway, yeah, there's nothing. There's no point where the derivative is undefined. So this is my only critical point. All right, and then the next step then is just to evaluate the function. Now we're going back to f, right? We're trying to find the maximum and minimum values of f, the original function. So the endpoints, we have one endpoint at 0, right? So if I put in 0, I get 0 minus 1 squared, which is just going to be 1. Okay, so that's the value of the function at 0. Now, let's see, the next point on the domain is just going to be at 1, right? That's my critical point. And so there I'm going to have 1 minus 1 squared, which is just 0. And then f at the other endpoint is, oops, not 4. Let's do 3. Let's do 3, right? That's the other endpoint on that closed interval. But when I put that in to the function, I get, let's say, 3 minus 1 squared, which is 2 squared, which is 4. Okay? Now, now I just need to identify the absolute maximum and the absolute minimum. I'm looking at the values of the function. It looks like the absolute maximum, so I'm going to write absolute maximum, maximum, come on, maximum, is at the point 3, 4. 3. Oh my gosh, this drives me nuts. 3, 4. All right, that's where my absolute maximum is. All right, because that's the highest value of f, right? And so the absolute minimum, oh my God, minimum is at, the lowest value of f is 0, right? So it looks like at 1, 0, that's my absolute minimum. All right, so that's the first one. All right, let's take a look at the next one. F of x is equal to x cubed, and we've got this closed interval from -2 to 2, and we want to find the absolute maximum and the absolute minimum of the function. All right, so the first step, find the derivative. F prime of x is equal to 3x squared. All right, so set that equal to 0, and we find that we have a critical point at x equals 0, right? Because when x is 0, then the value of the function, or the value of the derivative, is 0. Okay. So now that we have the critical points, we also want to look for any points where the derivative is undefined, and there are none. It's just a polynomial, or it's 3 power function, right? 3x squared. So there's no x values that are off limits. So so we don't have any other critical points. And then we want to evaluate the endpoints and the critical points. So one endpoint is at 2, and when I put a -2 and cube it into the value of the function. Now I'm putting it in the original function, so I'm taking -2 and cubing it, putting it back in the original function, and I get a -8, right? And then I'm going to evaluate the critical point, which is at 0, and I cube 0, and I get 0. And then the value of the function at the other endpoint, right, at 2, and I cube 2, I get a +8, okay? So now I just need to look at those values to find the biggest one and the smallest one, right? This is the minimum of all of those values, and this is the maximum of all of those values, right? So that's all I'm really doing here. So now I'm just going to state my final conclusion, which I have an absolute maximum. Oh, for goodness sakes. Maximum at, okay, so the x and the y coordinates are 2, 8, right? And then the absolute minimum is at, oh, for gosh sakes, all right, is at -2, -8. Okay, so on that closed interval from -2 to 2, the absolute minimum and the absolute maximum are both at the endpoints. All right, we got a couple more here. C. Okay, now this one's a little different. We have a absolute value function, And so remember that that just means that we can define it as a piecewise function, because how do we take the derivative of an absolute value? We haven't learned how to do that, right? But if we define it as a piecewise function, it's equal to x for x greater than 0, right? Because when x is positive, we can just leave the value as it is. And it's equal to negative x for x, okay. All right, for x, oh, come on, for x less than 0. Okay. Okay. So now I think I think that this one is actually included. But when we take the derivative, we can find f prime of x, right? We take the derivative of this thing, and what do we get? We take the derivative of x and we get 1, right? So the slope is 1 when x is greater than 0, and it's equal to minus 1 for x less than 0. Now you notice that the derivative has a discontinuity at 0. So you notice I didn't include 0 in either one of these intervals. We have this discontinuity at 0, so the derivative does not exist at 0, right? So I can say f prime at 0 does not exist. Okay, so that's a critical point. We have a critical point. I have a critical point at x equals 0, right? Because remember, we defined the critical points to be either where the derivative is 0 or where the derivative does not exist. So we do have a critical point at x equals 0. And now we just need to evaluate the critical points and the endpoints and pick the maximum and minimum. All right, so I'm going to first of all evaluate f of negative 1, right? F of negative 1 is 1, right? Because it's just the absolute value function. F at 0 is equal to 0, and f at 1 is equal to 1 as well, right? So so you can see this is a maximum, this is a maximum, goodness, maximum, and then this is our minimum. So I want to state my final conclusion then is that I have an absolute maxima. Now I have two maxima, right? That's plural this time, at negative 1 comma 1 and 1 comma 1. And I have absolute minimum, this is just one of these, at 0 comma 0. Okay. All right, we got one more. It's getting kind of long to do all of these in one video, but let's do this one more. This one's an interesting one. All right, so we have this function x to the 2/3 power, and it's defined from -8 to 8, and this closed interval from -8 to 8. All right, so first thing is to find the derivative. Okay, so we're just going to find the derivative, and we get 2/3 x to the -1/3. Okay, now let's, okay, -1/3. Now let's rewrite that. This is the same thing as 2 over 3 times the cube root, 3 times the cube root of x. For goodness sakes. All right, cube root of x. 3 times the cube root of x. Okay, did I get that right? Now, if I try to set that equal to 0, it's never equal to 0. It's never equal to 0, right? Because there's nothing I can put in for x to make that 0. But there is a point that doesn't exist, right? If I f prime of 0, right? If x equals 0 would not be in the in the domain of this function, right? I can't divide by 0. So f prime of 0 does not exist. Okay, so I have a critical point at x equals 0. Okay, right? So remember those two criteria: either the derivative is 0 or it doesn't exist. And in this case, we have a point where the derivative doesn't exist. And again, now that we have identified the critical points, we're just going to evaluate the function at the endpoints and the critical points. So we're going to put in a -8. And remember, we're going back to the original function. -8 to the 2/3. Okay, what the heck? Now you could use your calculator on this. But you can do this without a calculator because it's just the cube root of 8. Come on, cube root of 8 squared, right? That's the same thing as a 2/3 power, right? It's a 1/3 power squared, right? So so I can find that the value here, the cube root of oops, it should be -8. Cube root of -8 is a -2, but then when I square a -2, I get 4. Okay, because 8 is a perfect cubed. It's 2 cubed, right? So the cube root of 8 is 2, but cube root of -8 is -2. All right, square it, you get +4. All right, let's do f at 0. F at 0 is just 0 to the 2/3 power, which is 0. And then f at +8. Again, we're going to, come on. All right, we're just going to take the cube root of 8, for gosh sakes, and square it, which gives us 4 again. All right, so final conclusion is that we have an absolute maximum, at absolute maximum, we have 2 of them, right? We have 2 of them because it reaches a value of 4 at 2 different points. So our absolute maxima are at -8, 4, and +8, 4. All right, and then our absolute minimum is at 0, 0. All right. So that's all I have for this section, and I'll see you in class.